In a previous video, we described a hybrid method to select features by recursive feature elimination. In this method, we ordered the features by importance from the most important to the least important. Then we removed one feature at a time, starting from the least important feature, and we would keep the feature if the drop in performance after removing it is substantial. We implemented this manually, but we can actually automate it utilizing Feature Engine. In particular, we would need the Recursive Feature Elimination class. We will first start with a classification example, so we load the dataset and divide it into train and test. Then we create a pipeline to remove constant and duplicated features. We went over this code previously, so I'm going to jump straight ahead to the Recursive Feature Elimination. We need a model that we're going to use as a proxy to determine model performance. So in this case, we're going to use a gradient boosting classifier, but you can build any classifier that you want. And then we select the recursive feature elimination. We evaluate all the variables in the dataset. Then we pass the model that we want to use, the metric that we want to evaluate, and the threshold. This is the minimum performance drop that we need to obtain in order to select a feature. And this recursive feature elimination class utilizes cross-validation, so here we indicate the cross-validation fold. When we implement fit, what this transformer does is what we discussed in our previous video, but with cross-validation. So it fits the model with all the features, it derives feature importance, it orders the features from the most to the least important feature, and then starts removing one feature at a time and determine the performance drop. If the drop is bigger than the threshold, then the feature will be retained. All of this happens under the hood during the fit method. And after this, we can find some new attributes, for example, the initial model performance. This is the performance of the gradient boosting classifier utilizing all the features. The feature importances derived from these gradient boosting classifiers, which we can plot from the least to the most important feature. Then we also have the performance drifts for each feature. This is how much the model performance decreased or maybe increased after we remove the feature. And here we can see that most features cause no drop in performance, but there are a few that actually do, so those will be the ones that will be selected. In the features to drop, we will find all the variables that will be removed, and then we transform, we go ahead and remove all these variables from the original dataset. We can then build a model using only these selected features and compare the ROC-AUC that we obtained here with the initial one, and we see that it's very similar. So removing all these features did not cause a drop in performance of the random forest. We can go ahead and do the same in a regression scenario. So here we load the house prices dataset. We work only with the numerical variables, separate into train and test. And then again, we set up a model, in this case, a regression model. I use gradient boosting regressor, but you can use any regression model that you want. And with the recursive feature elimination, we pass now the new estimator and the metric that we want to evaluate, in this case, the R-square. And with fit, it trains the model with all the features, then orders the features by importance, and then starts removing one feature at a time, starting from the least important, determining the performance drop. And if the drop is bigger than our threshold, then the feature is retained or selected. Here we can see the initial model performance, the importance of the features, the drifts in performance after we removed each one of these features in the plot, and the list of the features that will be removed. With transform, we remove the features from the original dataset, and then we can build a new model and determine the R-square and compare it to the original one. And we can see that actually the model with less features has a higher R-square than the original one. That is all for this video. I hope you enjoyed it, and I'll see you in the next one.